I'm Mr. Blanchard, and today I'm going to show you how to use trigonometric ratios to find side lengths in right triangles. I suppose, up until this point, the only way that you knew how to find a missing side length on a right triangle was to apply the Pythagorean theorem, and for that you would have needed two sides of a right triangle. Trigonometric ratios let us use one of the acute angles and one of the side lengths in a right triangle to find any of the missing side lengths. So, in a problem like we have here, where we're given a 58-degree angle and a side, one of the legs, that's 12 units long, we can use trigonometric ratios to find the other two missing sides. Let's start by finding the other leg here. We've already learned the mnemonic device SOHCAHTOA to help us understand what the different ratios represent. In this case, we have the 58-degree angle and the adjacent side. We're looking for the opposite leg over here. We'll call that x for now. The ratio that relates the opposite side and the adjacent side is tangent. Tangent is opposite over adjacent. So, in order to find x, we'll use the tangent ratio. The tangent of 58 degrees is equal to the opposite side, x, over the adjacent side, which is 12. To solve for x, we just need to apply a little bit of algebra then. We'll multiply both sides of this equation by 12. So we do 12 times the tangent of 58 degrees is equal to x. And the tangent of 58 degrees is a known value. We'll use our calculator to get that value, or you could use a trig table. So if I take my calculator and do 12 times the tangent of 58, it tells me that that length, x, is about 19.2. And now we've found that side length. In order to find the other side, the hypotenuse, we'll call that y, we need to use a different one of our trig ratios. We'll still use the 12 and the 58. I don't want to use the 19.2 since I've rounded that, and that could make our values be off by a little bit. So we need to identify which one of these trig ratios relates the 12 and the y. Again, the 12 is the leg adjacent to our angle. So cosine relates adjacent to hypotenuse. So we'll use the cosine ratio. The cosine of 58 degrees is equal to the adjacent over the hypotenuse. So 12 over y. Notice that this is slightly different than our previous problem. On this example, the variable was in the numerator, and on this one, the variable is in the denominator. This is not trivial. This affects the way that we solve the problem. Here, in order to solve for y, we need first to get the y out of the denominator. So we can multiply both sides of this equation by y. And we get that y is equal to, y times the cosine of 58 is equal to 12. I still want to know what y is, and now it's attached to this cosine 58. We'll divide both sides of the equation by cosine 58. So y is equal to 12 divided by the cosine of 58. Now we have an equation solved for y. Again, the cosine of 58 is a known value. We'll use our calculator to figure out what our answer is. So in the calculator, I do 12 divided by the cosine of 58 degrees and hit enter, and I get that this length is about 22.6 units. This has shown us now both possible cases that we could encounter when working with these trigonometric ratios. Either I'm going to have the variable in the numerator, in which case I multiply both sides by the denominator, or I'm going to have the variable in the denominator, in which case what ends up happening essentially is that these two values, the trigonometric value and the variable, trade places. That is, the y comes to this side and the cosine 58 happens down here. We can see that in this expression here. You can use these models now to solve for any other problems where we're given one of the acute angles and one of the side lengths in a right triangle. Thank you very much.